Hi everyone, we're back for another lecture on our 2ME301 course. This time we're going to talk about statistical inference and some ways of computing how wrong you are when you actually do the inference by using a sample in order to infer something from your population. Let's start by doing a quick recap of some of the things we've seen before. Just to make sure we're on the same page here, we're talking about just a sample study for now. We're not talking about observational studies or experiments. So we're not talking about two different variables at the same time. We're only talking about what happens when you gather one single sample, so like one single data set, and how you use that in order to infer something from your population. And then we're going to build up on that in order to determine what happens when you actually have two variables, right? So it's the leftmost side here, which is the simplest also. So we start from there. Now we saw that the first thing you do after you actually gathered your data, of course, always considering all those things that we have considered about, random sampling and everything, the biases and so on and so forth. But let's say you actually went out there and you actually extracted your sample. So you have one data set. Well, we discussed that the usual thing is to, first of all, extract the mean, right, of this sample. And the mean is sometimes called mu, like the Greek letter mu, when it's regarding a population mean. And it's also simply called a sample mean when you're actually taking that from the sample, right? So in this case, in your case, most commonly it's just the sample mean, because you're just taking the mean of your sample that you gathered out there. So that's the most common descriptive statistic of a distribution, as we've seen before, and that's the number you should use if you need to describe your data with only one value. That's it. So basically the formula is this one. Of course, you don't need to really do that by hand because it's everywhere, but it's interesting to know that it's just simply obtained by summing up all your data values and then dividing by the actual number of values that you have. That is your average. And the sample and the population mean are computed in the same way, which means that's basically the same formula for both the sample mean and the population mean. Of course, most of the time, 99.9% of the time, you're not really computing a population mean because you don't know the population. It's just, let's say, a theoretical definition of the fact that they are actually the same. But most of the time, you won't compute anything about a population directly because you don't have the population, right? That's the point. The point is that you're trying to infer the population from the sample. So basically most of the time for you, I guess all the time is you're always computing a sample mean and never a population mean. Now, we've also seen that the mean by itself is not representative enough to be just used by itself, right? Well, at least it's not that it's not representative enough, but most of the time it needs to be followed by some kind of notion of how much the data actually varies around the mean, right? So we call that a variance or the standard deviation. Both things are related to each other. In our course, we're only talking about standard deviation, not variance. But basically, this is a measure of how much the data actually is spread around the mean. Because if the data is not very much spread, so if the data is actually very close to the mean most of the time, that means that your mean is a little bit more representative of your data set, because just by knowing the mean, then you know more or less how the data set is, right? Because all the data points are very close to the mean. But on the other hand, if you take the mean and you get a certain mean, but actually when you compute your standard deviation, you realize that the data that has a large standard deviation, so that the data is very much spread around the mean, there's a lot of variance, then that is good to know, because then you can expect that that mean that you just reported on your data is maybe not that representative, right? So that's the point of knowing the standard deviation. Of course, there's also the point that we're going to use it for computing other things later, but just to take it as it is, That's what it means. It means that a high standard deviation means that your data varies a lot around your mean. So that's also good to know when you're reporting the results of your whatever it is that you're doing, be it the data gathering that you're doing now or the results that you're going to get from your thesis later. And one interesting thing to know here is that the formula for the standard deviation in for the population, which means like when you actually know all the points that you have, is this one on the left. But actually when you have a sample, when you take a sample and you're trying to estimate the value of the standard deviation from the population by using the sample, then actually the formula that you should use is this one. And the only difference here is that instead of taking just 1/n here, which would be like the population size, when you're actually doing it in the sample, you do it 1/n minus 1. So you take one point away, so to speak, from your sample in order to divide, so that in order to compute like the size of n here that you're dividing for, because of some reasons that are really not that important for us. It's just important to know that if you actually had, in a perfect world, which you don't, all the points, then you would compute that using this formula over here. But since we never have that, we never have the actual whole population at our disposal, because if we did, then that wouldn't be really statistics. That would be just like stating a number, a known number. Since we don't have that, then it's very important to understand that whenever you take a sample and you're computing the standard deviation of the sample and you're trying to infer the actual population standard deviation from the sample, then this is the right one to use. It's 1/n, which is the sample size, minus 1. And there are mathematical reasons for that, because this one, by doing this, you're closer to the actual population mean. But it's really not that important for us right now. It's just important that you know that this is the actual formula. So you're basically just squaring the difference of every point to the mean. So like take every point, take the difference of that point to the mean, square it, and then sum everything and divide. So that's like how much on average these values are deviating from the mean, right? And then we realized that, you know, the reason why that's important is because you can have very different distributions like this too, that have the exact same mean, but very different standard deviations. And the standard deviation then brings that up to us, right? It tells us that these two things are very different, even though they have the same mean. And as we discussed, it's always good to, whenever you're reporting on your results that you've measured, whenever possible, and most of the time it is possible, you should also report on the histograms of the distributions, because the histogram of the distribution gives you a visual fingerprint to your distribution, and it also carries with it a lot more data than, not data, but a lot more, let's say, insights and information about the distribution than simply using two numbers, right? The two numbers are important because we use them to compute stuff, but reporting on the histogram gives a much more complete, let's say, report on the data that you've gathered. Okay, so it's always interesting to have them as much as possible. But so these are all like a quick recap, right? We've seen this before, but the point here that we have is that all these things, they're basically giving us information about the sample itself, but not of the population. Basically, we're measuring the sample, right? We're measuring the mean of the sample and the standard deviation of the sample. And I mean, these are just information about the data that we have at hand, right? They're not necessarily information about the actual population, which is what we want to do, right? So if you consider that there's this arrow back here, after I have a population that is somewhere, I sampled it, I have my sample, and then I measure my sample, but of course I want to go back, right? I want to be able to, from the sample, to infer the values of the population. So how do we do that? Well, we also went through this before quite quickly, which is that the sample mean is a good estimate of the population mean. So you can kind of trust that whatever mean you computed for your sample is usually a good estimate of the population mean, and that the standard deviation of the sample, which is again the one thing that we just computed, this one here, the right hand side, it can also be used, but with one small adaptation, right? Which is the fact that we're dividing by n minus 1 and not by n. First, because we don't know the n of the population. Second, because we only know the sample size, and the sample, in order for the sample's standard deviation to be correct, we need to do this small adaptation. So it kind of like, it kind of closes the cycle a little bit when we say, look, we measured it, we took the mean, we took the standard deviation, and now we're inferring back the values of the population. So we kind of close the cycle by doing this. However, this is not all, and it cannot be all, because if we think about it, like, how can you be sure about this, right? The right question to ask yourselves right now, after you've done all this, after you've closed the cycle, so to speak, by taking these measurements and by kind of inferring the population measure from that, the next question you should be asking yourself is, how can I be sure of this? How wrong am I with this? And of course, there is some kind of error, right? It has to be, because you're sampling this gigantic, let's say, distribution, or just gigantic population, be whatever it is that you're measuring. The point that you're doing statistics is because the population is too large to be measured as a whole, right? That's the point of doing statistics. So you, by definition, we assume that the population is too large. And how can you take a population that's suddenly too hard or too large to be explored? Then you take like 30 samples, you measure this, and that's it. Like, you've completely inferred the value of the population. Of course, there's an error involved, right? I mean, we expect that there will be an error. The point here is not that the error exists, because it will exist always. The point is, how can we have information about this error? So how can we define the boundaries of this error? That's the point. I would say that's the beauty of statistics, and that's the point that statistics exists, or else why would it exist, right? I mean, if you just took the sample and that's it, you don't have to do anything else, then that's it. You don't need anything else. You have it. You have your answer. You would, right? If that was the case, like if the sample mean was a perfect representation of the population mean, then you wouldn't need anything else. So the beauty of statistics is exactly the fact that you don't have that precise answer. So that's where statistics really starts to shine, which is when we can actually look at something that is unknown and establish, let's say, a boundary for that, an expectation for that error. I know that there is error, but I expect that this error is going to be between this and that. I don't expect the error is going to be infinite, right? If I expected my error to go all the way from 0 to 10,000, and if my mean is 100, okay, well, my mean is 100, but it could be anywhere between 0 and 10,000. Then that would be completely useless, right? Your statistics in this case would be completely useless, because it was basically random. You could just take a number out of your pocket and read something that's in there, and you say, this is what I measured, because it wouldn't make any difference. So we will establish now, or I will show you how and why we can establish these margins of error, let's say, as you can see in this picture here, so that you can have an idea of where more or less your error is contained in. And in this case, it's just like a very simple example of a poll that was made in the United States before the election of Trump for the first time, and when he was running against Hillary Clinton. And then the center of these two distributions basically is basically the mean, like something you would have measured, right? So 43% or 42% of people want to vote for Hillary and 43 for Trump. But as you can see here, they have established this kind of like margins of error. So they expect that, well, it's 43%, but they expect it to be like -3 or +3 points or percentage points. They expect that to be the case. So it could be somewhere between 40 and 46. And we really don't know. We know now that this is correct because Trump won. But I mean, if they were wrong just by 1 point to the left, and they were wrong about Hillary Clinton just 1 point to the right, then it was still believable that Hillary could have won at that point when we didn't know, because the errors, the overlap of these distributions, if you look at it, there's a full overlap between 40 and 45 is so large here. The overlap is so large that it's just impossible to, it was at that time impossible to have a very good estimate of this, simply because there was a lot of overlap. And as we will see later, when we actually talk about two different variables at the same time, this overlap between these two things, this is very important, because the smallest, the largest the overlap, the less we know about it. And when the overlap becomes very small, then we kind of can have much more, certainty of the differences between two things. But anyway, we start with the case where we're measuring just one thing, and we're going to try to determine this. And for that, I need to talk about something called the sampling distribution, which is what we're going to do next, which is a beautiful concept from statistics, and I hope I can communicate that clearly to you, because it's very important, and it's also something that you're going to use always whenever you gather data about anything. Well, not always, but it's a very nice way to report on the results that you have. And if you're not using it, then I guess there's something wrong, because you should. So the way that I'm going to talk about the sampling distribution is by using this abstraction that I've created of the perfectionist researcher. So let's say that someone is doing research, like you guys are doing the data gathering, right? This person is doing a research about something, and the way that he or she is going to do the research is by taking a sample of 40 people. So they're going to take a sample of 40 people and ask something like, what is your salary, or how many grams of meat do you eat per day, or something like this, any kind of a measurement, right? And they're taking that, let's say they take one sample of 40 people, a little bit like what you guys are doing. However, and let's say he does that, he takes a sample, measures 40 people, and okay. For most people, that would be it. However, this guy's a perfectionist, or this girl is a perfectionist researcher. He's not satisfied with that, because he took this sample of 40 people and he measured that, but he doesn't trust the results, because he said, you know what, I can't just use one sample of 40 people in order to determine the value for the entire population of Sweden, let's say, right? It's just too small. I don't trust it. I don't care about statistics. I don't trust it. So then the next day, he goes out and he does it again with 40 different people. So he takes another sample of 40 people, right? And he does the same thing. He asks for the same thing. So he's doing the exact same research, but with 40 different people. And then he finalized that. And okay, again, it's a new sample. He replicated. We call it a replication, right, of the research. So he replicated it. He got a new sample mean. He got a new sample standard deviation. So now he has two sample means, two sample standard deviations. And he's like a little bit more confident on the results, because they kind of look more or less similar. But he's still not happy. He's like, yeah, no. I mean, still, like, just 80 people in order to represent the whole population of, let's say, Växjö or Sweden, even Växjö. That's not enough. I don't trust my results. I need to keep on doing this research. So he or she's such a perfectionist that he keeps on going and going. I'm gonna say he. Sorry guys, it could be a she. It's just that I want to make this a little bit more straightforward. So he goes out and he keeps on taking more samples every day. So every day he goes out 40 people, and then the next day he goes out 40 people, and he keeps doing that, right? And every day that he does that, he takes a new sample mean and a new sample standard deviation. And actually, he's such a perfectionist that he actually does that 50 different days. So for almost 2 months, he's going out every day and taking a different sample of 40 people, right? Every day for almost 2 months. So what happens? What? Of course, let me make this very clear. This is not feasible, and this is just a theoretical exploration, right? You're not going to do this ever. Nobody does that. You don't replicate your own experiment or your own research 50 times. You don't. You just do it once, and if someone else wants to replicate it, that's fine. But usually people don't replicate the experiment themselves. And of course, there are cases where when you do, but not usually. So the idea here is just theoretical exploration. And he just does that. So the interesting thing here is that after he's done this like 50 times, so he took 50 different samples at 50 different days of in this case 200 or 2000 people, right? Not 200. So 2000 different people were involved in this whole thing. And the interesting thing about this is that if you or anyone does that, you will actually end up with a new data set, right? It's not just a data set with, like people. It's a new data set formed by 50 means, 50 sample means of 50 different samples. So now you basically have one new data set that's just mean after mean after mean. So every day is a new mean, every day is a different mean. And when you put them all together in one data set, then you have a new data set, which is just 50 sample means, right? So after he did that, then what he did was he took the mean again of this new data set. So it's like the mean of the means. And now he's satisfied with his results. Because now he's saying, look, I took 50 different means, and now I'm taking the mean of the means. And this is, for me, much, much more trustworthy than if I just took one sample and one mean of 40 people. Now, again, of course, you're never going to do this, but in theory, what he did was actually a good thing, or it was like right, because of something called the central limit theorem, which is something I'm going to discuss with you. But I just want to make sure that this idea sinks in right now, this theoretical impossible idea. Instead of just taking one sample, you take 50. Then from these 50 different ones, you take 50 different means, or 30 or 40, it doesn't matter. Now you take these means, you form a new data set, and you take the mean of these new data sets. So effectively, you're taking the mean of the sample means, okay? Suppose you did that. If you did that in an imaginary world, in theory, that would be right, a right thing to do, or the good thing to do, because of something called the central limit theorem. So what is the central limit theorem? In a very overall simplified manner, the central limit theorem says that if you take many samples of the same population, and which is the case in this case because he just replicated the same experiment over and over again, so the population from which he took the samples was the same all the time. So if you do that, by definition, or it can be mathematically proved, that the mean of the sample means, the mean of this new data set that you made with the sample means, will converge to the population mean. So the mean of this sample means is an even better estimate of the population mean than just any single sample mean that you took individually, right? And the distribution of all these sample means that you took, they will be approximately normal. We already talked about normal distributions. We're going to go back to that. But if you guys remember it, it's simply like this kind of like bell-shaped distribution. So what's cool about normal distributions, and what's cool about the fact that the sampling distribution is normal or approximately normal? The cool thing is that normal distributions are in general the data points are very close to the mean. So the mean of any normal distribution is very representative, right? If I take a normal distribution like this, whatever it is, and I take the mean of this normal distribution, then that is a very good representative point of the mean of the distribution as a whole. So if I say that the mean of the sample means will converge the population mean, I'm basically saying that the population mean is in the middle here of this distribution. And that is a very good, very representative point of the entire distribution. And the coolest thing about this is that the original distribution of the population does not matter. So for example, I'm going to actually jump to a website where I do this very interesting simulation. Let me zoom in this a little bit. Yeah. So this is a simulation of this thing, of this idea of the sampling distribution that we've been discussing. Let me explain what's happening here, and then I will run the simulation. First of all, this is the parent population, right? So I can change this. I can do whatever I want here, right? Let's say this is the distribution of your population, right? I guess it's a little bit too much. So let me just do something a little less chaotic like this, just so we can see some nice results. So let's say that this is the population distribution. Now you don't know this, okay? I don't know this. Nobody knows this. Let's say this in theory, this is what the population distribution actually looks like of whatever it is that you're doing. Like, you know, how many grams of meat every person eats per day. Let's say this is the distribution. There's a lot of people that eat something here, then it goes down, then goes up a little bit, then goes down and goes up a little bit. I know there are like 3 profiles of people: those who eat very little, those who eat very much, and those who eat something in the middle. I don't know. But let's just suppose or assume that the population distribution is completely like irregular. It's not really something that's easy to predict. It's not normal. It's not anything. It's just some irregular distribution. Now, suppose that I go and I take one sample, and for some reason I can only go up to 25 here, so I'm going to use 25. So then let's say I go out there and I take a sample of 25 people, and I ask them, how many grams of meat do you eat per day? So here's the process of taking the actual 25, the actual sample of 25 people and ask them, blah, blah, blah. So we took that, and then we took the mean of this sample over here, like one sample, one mean. That's what you have here. Basically, this is where you stop normally, right? In any kind of experiment, like the one that you guys are doing now. Basically, that's where you would stop. Okay, I took a sample, I took the mean, and that's it. But suppose that we keep going, right? Suppose that I go out there and I take another sample of 25 people. Well, that will give me a new mean, right? Yeah, that's it. Now I have 2 means. I have this one and I have this one. Sure, I took 2 samples. Now let's say I go out there and I do the same thing. So now I'm taking a third sample of 25 people and ask them, well, how many grams of meat do you eat per day, blah, blah, blah. I got another mean here. So now I have 3 means. And as you can see, I'm kind of forming a new data set, right? So I could go on and I could take 5 more, like 5 more days, and then 5 more days would represent 5 more means here. 5 more days, 5 more means, 5 more days, 5 more means. And I can just go on and go on and go on. And if I did that 10,000 times, for example, let's say I took, of course that's not possible, but I mean, I went out there and I replicated my experiment 10,000 times. Now look at how beautiful this thing looks. The distribution of means here, or also called the sampling distribution, is very, very approximately normal. And not only it is approximately normal, but it is centered around the population mean, which is cool, right? Great. So the important part that you must understand from this is this sampling distribution, which is theoretical, we don't have it, it is normal. Okay. Now you might be thinking something like, yeah, well, who cares, right? Who cares if this sampling distribution is normal if I can't have it? Because I'm not going to go out there and take 100 samples, or I'm not going out there and I'm not going to replicate my sample 10,000 times, right? Well, yeah, that's true. You're not going to do that. But remember what we know about the normal distribution. So we don't need to have a normal distribution in order to understand how a normal distribution works, because we know how a normal distribution works anyway, right? So even if we don't have it, we know that, for example, you have the empirical rule. You know that 68% of the data is within one standard deviation of the mean. And we know that around 95% is within 2 standard deviations of the mean. So even though we don't have this distribution, we know that our sample mean, our single sample mean that you just went out there and took just one, which happens to be this X bar here over here, we know that it is in there somewhere, even though we don't have the full distribution, right? We know that this sample mean here is in there somewhere, because it is part of the sampling distribution, right? If we took 1,000 samples, then we would have distribution. But since we only took one, well, it's still one sample mean, and we know that it is in there somewhere. And since we know how the probabilities here, then we know that there is, for example, we know that there is a 95% probability that our sample mean, the one that we actually measured, is within 95%, well, sorry, is within 2 standard deviations of the center of the population, or of the center of the sampling distribution, which we don't have, right? So you see, it's like an abstract thinking right now. There is this abstract distribution that we don't have, but we know the shape, and the shape is normal. We know that the center of the sampling distribution here is the population mean, which again, we don't know, but it is there somewhere hidden away from us. And we know that this one sample mean that we just took is in there somewhere. And there is a 95% probability that it is within 2 standard deviations of the actual population mean, because it is, you know, the population mean is the center of the distribution. We have established that. And that's where the concept of a confidence interval comes from. So if we could build this confidence interval, or the sampling distribution, which we can't, we would see that it is a normal distribution. We would see that it is centered around the population mean. And by knowing that, we would know that our sample is inside there somewhere. And there is a 95% probability that it is within 2 standard deviations of the actual center, which happens to be the population mean. So look how cool that is. Because the fact that this thing is a normal, the fact that this abstract theoretical confidence interval is normal, that allows us to set up this boundary of this error. So I'm basically saying that any sample that you take, any single sample that you take, be it the one that you took or any other, which is what like people do when they go out and they ask people, who are you going to vote for example. You go out and you take a sample, any single sample that you take, any, has a 95% probability of being within 2 standard deviations of the right answer. Just take a second now to think about it, how nice that is. Because we know the shape of normal distributions, because we know the probabilities of normal distributions, because we have the empirical rule. And actually, we don't have only the empirical rule. Just so you guys know, we can actually compute the probability of any point in this curve. Any point, if you put your mouse anywhere, I can tell you what is the probability of that point or something around that point to happen. Any point in this entire curve. So the normal distribution is a great thing, because as soon as you know that something is normal, you can determine the probability of anything happening within that curve or that distribution, or however you want to call it. So let's see if that sinks in. We take a sample, any single sample, whatever, and by definition, in a way that can be mathematically proven, that sample that you took has a 95% chance of being within 2 standard deviations of the actual population mean. So now we've defined our boundaries, okay? However, there is one thing that's missing in this entire thing, which is the standard deviation of the sampling distribution. Now, let's recheck our terms here. We have the standard deviation of our sample, right? That's okay. That's perfect. You have your sample, you've measured the standard deviation, and it's there. However, that's not the same as the standard deviation of the sampling distribution, right? Because we're talking about this sampling distribution as this imaginary thing that we don't have it. We don't have it at hand. We know it exists. We know it's there, and we know it's normal. But just by knowing it's normal is not enough. We need to, and again, we know that it is centered on the population mean. But of course, in order to define a normal distribution, we need 2 things. We need the center, so the center is somewhere, and then we need also like how wide it is, and that is usually by the standard deviation, but not the standard deviation of your sample, and also not the standard deviation of your population. It's the standard deviation of this specific distribution that is a separate thing. And it turns out that there's a very easy way to approximate that, which is by taking the actual standard deviation of your sample, whatever it is, and dividing it by the square root of the size of your sample. So it's basically like you take the standard deviation of your sample and you divide it by the square root of the number so that it actually becomes smaller. And that's really good, because the smaller, like we saw so many times, the smaller the standard deviation, the more trust you have in whatever it is that you're using the mean to represent, right? The smaller the standard deviation means that your mean is more and more representative. And since you take your sample standard deviation and divide it by the actual number of points, so the larger the sample, the smaller is the error that you have when you're estimating this confidence interval. And that's why sometimes people say, well, you know, the larger your sample, or the more people you ask, for example, in the street, or the more data points you take for whatever it is that you're doing, the better it is, because your error will get smaller and smaller and smaller, following the square root of the size of your sample. So again, the larger the sample, the smaller the error. And how does that actually translate to something that you can use in practice? Well, it translates to the fact that this imaginary or abstract sampling distribution that we have created, it becomes narrower and narrower and narrower. The smaller the standard deviation, the more the data points get closer and closer and closer to the mean. And when they're very close to the mean, then that means basically that the points are, they are very close, they are very similar to the mean. So any point that you take, any single sample that you take, will be very close to the mean. And that translates to the fact that your estimate is much better. And also the margins of error that you have are much better. So basically that's it about the sampling distribution. You need two things to define the sample distribution. You need the center of it, and the center of it, you can estimate it using the sample, because you take the sample mean, and as we saw before, the sample mean is a good estimate of your population mean. And then you take the standard deviation of the sample, but you cannot use it directly, right? You have to divide it by the square root of the number of points you have, and that's it. Then you end up with some kind of a normal distribution. And then by using the empirical rule, you take, okay, since I know from the empirical rule that when a distribution is normal, 95% of the points are within 2 standard deviations plus or minus, right? Then I can say, well, this sample that I just took, this mean, is within 2 standard deviations, or sorry, 2 standard errors, as it's called. As I forgot to say that, sorry. When you divide the standard deviation by the square root of n here, it's not called the standard deviation anymore. It's called the standard error. That, which is nothing more than simply the standard deviation of the sample distribution. It's not like a different name to use in order to not mix up both things. So the standard error is the standard deviation divided by the square root of the number of samples you have. So basically, if we go back, what I mean here is that I took a sample, I took the standard deviation of my sample and the mean. Then I compute the standard error and I say, okay, I know that my mean is within 2 standard errors of the actual population mean. Well, I have 95% confidence in that, right? And this is how you set up your margin of error. So that's basically that's it. The sample mean plus or minus 2 times the standard error, that will give you the 95% confidence interval, not 100%, right? And actually, if 95% was like too little for you, and you want to be 99.7% sure of what you're doing, then you can simply use 3 times the standard deviation. The trade-off here is that you're also making the interval, your margin of error is larger, right? So I mean, if you want to be more certain that your mean is somewhere in there, then you're gonna make the interval larger, because then you kind of like get more possible data into it. But then you're more sure that it is actually in there. So it's a trade-off. Usually 95% is enough. So that's usually how you do it. Now, for example, take this drawing here that I took from this site, simplypsychology.org. This is the representation of a sampling distribution. It's a normal distribution. We don't have it, but it is there somewhere. It's just hidden away from us. So for example, the mean here is 4.27, right? Then, and the mean is in the middle here. So then we say, okay, there's a 95% chance that your population mean will fall between 2.92 and 5.62. Well, because this mean here is actually an estimate that we did using the sample, right? So I mean, my sample mean is 4.27. I don't know my population mean, of course, because we don't know. We estimate it from the sample, right? We never know the population values. We're always estimating. So if I took my sample mean here and it's 4.27, this is the center of my sampling distribution. I know it's normal, and they computed it here like somehow it doesn't say here what is the sampling error, or sorry, the standard error. But it's half of whatever's the difference here between the mean and lower limit and the upper limit. But anyway, the lower limit is 2.92 and the upper limit is 5.62, because they took the mean minus 2 times the standard error that was computed like this, that is 2.92. And again, they took the mean and they make the mean plus 2 times the standard error, that goes to 5.62. So we can say there's a 95% chance that the actual population mean is inside this interval between this and this, because we know that this is how the normal distribution works. And then there are 2.5% of outliers over here and 2.5% of outliers over here. So why is it 2.5 and not 5? Because if you sum this one with this one, that makes it 5%. And since we have 95% chance that your population mean is inside this interval over here, then of course the rest of the other 5%, they are, let's say, distributed outside of this area. So half to one, right, and half to the other, because it's a symmetric distribution, right? So if the distribution is symmetric, then you know that it's kind of like half and half to each side. But 95% of the points are inside this area over here, and they will fall between 2.92 and 5.62. So that makes you quite confident about what you're talking about, right? That you have a 95% confidence, and that's where those margins of error came from. Like for example, with the Trump and Hillary ones, and that's how you are going to report your results also. So I'm going to just jump for the next one, and then I come back to that one. But this is a quick summary of what you can do with the confidence interval and how you report the confidence interval of your inference. So that's how you can report or communicate how certain you are about whatever it is that you've measured, right? So for example, you take your sample and you compute the sample mean. This is, I mean, you've seen this a million times before. Then you find the standard deviation also of your sample, which we call S, right? So you have the X bar over here, which is your sample mean. And then you have the standard deviation of your sample also, so S, this just the normal standard things that you take anyway, right? Then you find the standard error of your sampling distribution. Again, the sample distribution here is something abstract. You can't really see it. It's there, but you don't have it, let's say, in your hands. But you can compute the standard error, and the standard error is your sample standard deviation that you got here, divided by the square root of n, which is your sample size. So if your sample size is 30, then it's the square root of 30. So if your sample size is 25, the square root of 25, and so on and so forth. And that gives you then the standard error, which we call here sigma x bar. Just it's like an estimate of sigma using x bar, right? It's different sites, different books will call it different things. So we will stick to this one. So you got your standard error. Now you choose a confidence level. If we're using 95% confidence, if you want 95% confidence, then usually it's around 2. I say 2 usually, but just for simplification. But actually, most places you will see 1.96. Right? Well, most places will tell you that 1.96 is the actual like number of standard deviations that you can go away from the mean and have 95% of the data in that region. I usually say 2, around 2, just because it doesn't make that much of a difference. And with 2, you actually have more confidence. You have more than 95% confidence. Using 2 instead of 1.96. 1.96 is like a theoretical value that gives you exactly 95% confidence. But around 2 is, in practice, more or less the same. So you choose a confidence level. If you wanted 99%, 99.7%, then you would actually use 3. In practice, most of the time, it's around 2. And I will just call that alpha for the confidence level. We're going to use this later again. So I'm going to call it what I will call it later, and so in order to keep consistency. That's what I call my confidence level, right? That's how much confidence I want to have on my results. And now I'm ready to compute my confidence interval. So my confidence interval is the interval centered on my mean plus or minus the confidence level. So the mean is in the center of this interval. Then I take my plus or minus, I just kind of put them together here, plus or minus alpha times the standard error. So in practice, that would be the mean. So in practice, let's say the left-hand side of my interval would be the mean minus 2 times the standard error. And the right-hand side of my confidence interval would be my mean plus 2 times my standard error. So it's both, in both ways, it's the same confidence level. And that will give you some value on the left and some value on the right in the same way that you got here. So 2.92 is 4.27 minus, I guess 2 times whatever the standard error is for this distribution. And 5.62 is 4.27 plus 2 times the standard error with whatever it is for the distribution, which I didn't compute. But that's what you get. Then you have this confidence interval, and the way you actually represent your confidence interval is simply by giving the lower limit and the upper limit. So you say between 2.92 and 5.62. I'm 95% confident that my actual population mean is within that interval. And I like this picture very much, because it's a representation of what would happen, again, like what we did with that other simulation. It's a representation of what would happen if I actually took 100 samples of the same population, right? If I replicated my experiment 100 times, right? And every time if every time that I replicate my experiment, I go there and I compute the confidence interval using this scheme here that I gave you, then you would get these lines, right? You get the mean, then you get the left-hand side of your confidence interval and the right-hand side of your confidence interval by taking minus 2 times the confidence level or the standard error plus 2 times the standard error, right? So for every sample, you will have a mean and a confidence interval, a mean and a confidence interval. Then you take that, you do that 100 times, right? Let's say you replicate your experiment 100 times from left to right here, from 0 to like 99. The cool thing about this picture is that it shows that the true population mean, which is in this case 0 by definition, because this is a simulation, right? They know that it's 0. This true population mean, it ended up being inside the confidence interval for all but 4 of the replications. So the experiment was replicated 4 times and had 100 times. And there were only 4 times when the actual confidence interval that was computed did not include the population mean in that. So in that case, and these are the red ones, right? And in these cases, the red ones, like for example, in this case here, that would be a very bad sample. We wouldn't have any way to actually determine if it was or not. So maybe this is the sample that you take when you do your experiment. Too bad. There's no way for us to actually determine that, because you can't just go around replicating experiments forever, right? So you have to make one experiment, and then from that one experiment, you kind of go out there, take your confidence interval, and you say, look, this is my confidence interval. This is as much as I can do. But the whole mathematical framework and the whole statistical framework is behind you on that, is supporting you to say, look, maybe my sample is the 5% that are bad. Sorry, I cannot do anything about that. However, what I can say is that I have a 95% confidence that actually my confidence interval that I just computed includes the mean in it. So the mean is in there. Maybe it isn't, maybe, but there's a very low possibility that it's not really in there. Because out of 100 times, if I replicate the same method over and over and over again, in this case, only 4 times actually didn't have the population mean in there. And I mean, in general, like on average, that is 5, right? Because that's why it's like 5%. That's the meaning of 95%. 95% means I expect that if I replicate my experiment 100 times, 95 of them will include the true population mean. And that's what the confidence interval means. So yeah, guys, this is basically it for the confidence interval. I'm gonna actually, you know what? I'm gonna click on this link here because there's a very simple example here that I can show you. They're using slightly different notation. I hope it's not a problem. But basically, like this, there's an apple orchard, and I want to know, are the apples big enough? Like I expect the apples to be a certain size. I don't know what is their size, but I want to check. So I've had like lots of different apple trees, and I want to know how many, like what's the size of my apples, because I want to, like, I don't know, find out how many boxes I must buy, or I just want to maybe I tried some new different thing, and I want to know if the apples actually grew up to be better than before. Something. I don't know. I just want to measure how big are my apples, and I have hundreds and hundreds and hundreds, and I don't want to measure all of them. So let's say I just go out and I randomly pick 46 apples. I just go out and say, okay, this one, and then I walk couple of steps to the next tree, and I take this one, and I go all the way over there, take the next one, and so on. Let's say I do this and I took 46 random apples. Let's say that the mean of my then I measure them, right? There's 46 apples. I just take them and I measure them, and the mean is 86. And I'm a bit confused as to exactly what is this 86 that they're talking about here, because that kind of sounds weird. 86. I don't know what's that. And then our standard deviation of 6.2. So again, like always, take a sample, take the mean, take a standard deviation. Now, I want to calculate my confidence interval. And my confidence interval here is the mean plus or minus z, which in our case, I call z this sigma x bar. So z is a bit easier, right? They call it z because of the z value. We're going to see that later. Times the standard error. And as you know, this is the standard error, right? S divided by the square root of n, as we saw it here, right? So basically, if you change z to alpha, I'm using alpha, they're using z, then basically it's the same. It's the mean plus or minus z times the standard error. The mean plus or minus z or alpha times the standard error. Now, we know the mean, 86, that's easy. We know, like, the z, in this case, they're using 1.96, like I said, because they have a table that tells them that 1.96 is what you need in order to compute 95%. No problem. We're using 2. No problem also, because actually we're going to have a slightly more confidence in what we're doing. No problem. You can use 1.96 if you want. We know the standard deviation is 6.2. We measure that. We know the number of observations, which is 46. And so if you take this and you just put them all together and you put them in the same equation here and you replace everything, then you're going to end up with 86 plus or minus 1.96 times 6.2 divided by the square root of 46, right? Now, I don't know exactly why they chose 46. They could have gone with something easier, but anyway. So this ends up being 86 plus or minus 1.79, which is quite interesting, right? If you measured 86 and you only have this small margin of error of 1.79, then basically it means that the true mean of all the hundreds of apples, which is that thing we're trying to infer, is then likely to be between 84.21 and 87.79. And like I said, this is how you report on your confidence interval, right? You give the lower end and the upper end, let's say. The lower here is 84.21, which happens to be 86 minus 1.79. And the upper end here is 87.79, because that's what 86 plus 1.79 is. And then you can say, yeah, it's likely to be here. After all my computations, this is the best thing that I can tell you with a 95% confidence of where the true mean of the apples are. And then you can make whatever decision you want to make with this. Like, I don't know, I will just assume that the worst. So I will assume that my apples are 87.79, and then I'm just gonna buy like a certain number of boxes, so that if I was to have, you know, if I have like 500 apples with 87.79 size, then I need a certain number of boxes, so I will buy them. Or I will just take the mean of the confidence interval, which is just basically just 86, and I will consider that a guess. But I guess in that case, you wouldn't need your actually your confidence interval. So I would just prepare for the worst and assume that my apples are all 87.79, and I would buy as many boxes as are necessary for the harvest, or something like that. And that's it for the confidence interval. And I just wanted to make a small note that I expect you guys to report on the confidence interval in your results of your data gathering. Although some of you will actually have to report on the confidence interval, something a little bit more complicated, which is the comparison between two variables, right? Because some of you decided to do a comparison of two variables. But at any rate, even if you are doing a comparison of two values, I expect you to report on the confidence interval of each of the two measurements that you're taking. So if you're gonna like measure in the morning and in the afternoon and then compare them, before you compare, show me the distribution and the confidence interval for the morning and the distribution and the confidence interval for the afternoon, for the night. Independently, right? So we start by showing the variables independently, and then you show the combination in the second step, all right? And the confidence interval is probably the most important part of reporting on the data gathering of one sample individually.